Section 1.4, Real Numbers and the Number Line. First idea that we will use here is that of what's called an opposite. The opposite, or additive inverse, of a number a is written as negative a. So for example, the opposite of 12 is negative 12. The opposite of negative 45 is negative 45. Well, wait a second, we don't like negative 45. We would just write that as 45. The opposite of negative 45 is 45. The double negative rule then says, if a is any number, then the opposite of negative a is a. The opposite of negative 45 is 45, and in general, the opposite of negative a is a. Find the opposite of each number. The opposite of 23 would be negative 23. The opposite of negative 9 would be 9. The opposite of negative 15. This one's a little trickier. So let's just deal with this first. The opposite of negative 15 is 15. So then what is the opposite of 15 would be negative 15. Find the additive inverse of negative 37. Remember, additive inverse is another word for opposite. So find the additive inverse of of negative 37. The additive inverse of negative 37 would be 37. All right, so now we're going to add to our sets of numbers that we have discussed in this course. Earlier in the course, we talked about the natural numbers and the whole numbers. So now we will add to this by talking about what we call the integers. The integers are the set of number containing 0 and 1 and 2 and 3 and so on. But it also contains the opposites of the natural numbers. So it would contain negative 1 and negative 2 and negative 3 and so on. These are called the integers. And we will also talk about what are called the rational numbers. A rational number is any number that can be written in the form P over Q, where P and Q are themselves integers. These numbers are known as the rational numbers. So that's just the definition. And now we're going to show what are some examples of rational numbers and how can we determine if a number is rational. 5/7 is a rational number because 5 and 7 are integers. So this is a rational number. Nothing really to discuss here. It fits the form. -7 is a rational number because it can be written in the form -7 over 1. Negative 7 is an integer, 1 is an integer, so negative 7 is a rational number. And in fact, all integers are also rational numbers. Negative 12.6 is a rational number. If you think about what you may have learned in the past about decimal numbers, I could write this as negative 126 over 10. If you go through the division process, you'll find that this is correct. Negative 126 over 10 is negative 12.6. Hey, negative 126 is an integer. 10 is an integer. It's a rational number. And in fact, all terminating decimal numbers are also rational numbers. And 0.7 with that bar over the 7. Hopefully you remember that this means 0 point and the 7 is repeated over and over and over. And this one's a little trickier, but it can be shown, and you're not expected to know this, but it can be shown that this 0.7 repeating can be written in the form 7 over 9. And if you have a calculator handy, you could try this out on your own. Type in 7 over 9, and you should get a 0.7 repeating up until maybe the last digit that shows. It might round it up to an 8. And in fact, all repeating decimal numbers are also rational numbers. All right, so before we talk about what's not rational, let's talk about this thing called a square root. And hopefully you've seen it before somewhere along the lines. We say the number b is a square root of a if b times b is a. So we would say that 9 is a square root of 81 because 9 times 9 is 81. In symbols, we would say that the square root of 81 is 9. So that symbol means square root. And it's called a radical. All right, that symbol is called a radical. And so we would say is that the square root of a number is the principal or positive square root of the number. And we'll talk more about what we mean by principal and positive in a later chapter. So for example, the square root of 36 is 6. The square root of 121 is 11. The square root of 30, this one's tougher. 30 is not a perfect square, so the square root of 30 is difficult to find. Now, I've got a calculator handy, and my calculator tells me that the square root of 30 is 5.4772255575. But it's not exactly correct. In fact, this is only an approximation. This decimal number does not end, and it does not repeat. Now this can be shown using mathematics. I just need you to sort of believe me at this point that the square root of 30 has a decimal part that does not end and does not repeat. So now we can discuss what we call the real numbers and the irrational numbers. All of the numbers that can be represented as a decimal number, basically every number on the number line, is a real number. All natural numbers, whole numbers, integers, and rational numbers are also real numbers. However, some real numbers cannot be represented as fractions. They are called irrational numbers. So for example, the square root of 30 is irrational. We just showed that it could not be represented as a decimal number that ended or repeated, so it is therefore irrational. Pi is also an irrational number. It can be approximated as 3.14, but it cannot be written as a fraction where both the numerator and denominator are integers. Another example would be the square root of 2. Square root of 2 is approximately 1.4. That's just an approximation. It is not an exact value. So these are just a few examples, and there are other examples out there, but these are just the basic ideas that we need to get across. So in general, if the decimal form of the number terminates or repeats, the number is rational. If the decimal form of a number does not terminate or repeat, the number is irrational. All of the numbers on the number line, rational or irrational, are called real numbers. Alright, so let's consider this following list of numbers. The idea here is let's look at these numbers and figure out which ones fall in the different categories. Alright, so first, which, if any, are natural? So remember, the natural numbers are our counting numbers. 1, 2, 3, 4, etc. Now, some of these are in forms that are a little tricky to work with. For example, this one, the square root of 100, can be also written as 10. Hey, that's a natural number. So the square root of 100 is natural. 29 is also natural. Which, if any, are whole numbers? All right, so remember the natural numbers were the whole numbers were the natural numbers and 0. So whatever was natural is also whole. And we also need to remember that 0 is a whole number. Which, if any, are integers? All right, so remember the integers are the whole numbers and any opposites of the natural numbers. So if it was a whole number, it's also an integer. Square root of 100, 29, 0, and anything else, -9 is an integer. Which, if any, are rational? All right, so remember the rational numbers were any integers, and basically any number who had a decimal form that would terminate or repeat infinitely. But we know that anything that's an integer is also rational. Now, what about the others? -4.77, terminating decimal, rational number. We've already got 29. How about the square root of 43? 43 is not a perfect square, so it won't have a nice square root, so the square root of 43 is irrational. Hey, let's put it on the next list. Negative 9 is taken care of. 9 over 4. 9 is an integer, 4 is an integer. 9 over 4 is rational. Square root of 100 is taken care of. 6.123 with a bar on the the point 123, that's rational, a repeating decimal number. 0 is taken care of. 5 pi. Well, we know that pi is irrational. Any multiple of pi is also irrational. So 5 pi would be irrational. And which, if any of these, are real? All of them are real. Because they are either rational or irrational. We could plot every single one of these numbers on a number line if we really wanted to. Speaking of the number line, let's get some practice with it. Here we are asked to plot the following numbers on a number line: 7 halves, negative 2.7, and 9 fourths. All right, so let's get a number line on here. And let's see, 7 halves. Well, 7 halves we can show is the same as 3 and 1/2. Similarly, 9 over 4 is the same as 2 and 1/4. So if we wanted to show these on a number line, we would need to at least see where 3 is, maybe past 3. And we also have this negative 2.7. So let me put 0 here. There's my origin. There's 4. And there's negative 4. And plotting 7 halves, well, that's 3 and 1/2. So here's 3. So 3 and 1/2 is about here. And I will label it as 7 halves, the original number that was given. Or I should say the original form of the number. Negative 2.7, well, here's negative 1, negative 2, and here's negative 3. Negative 2.7 would be about here. And finally, 9 fourths is 2 and 1/4, so 2 and 1/4 is about here. And again, I will label it as 9 fourths, the original number that was given. Absolute value. The absolute value of a real number equals its distance on the number line from the origin, or 0. The symbols that we use have 2 vertical bars, and these bars are read as the absolute value of whatever's inside. So the absolute value of A is written here. So then what's the absolute value of 7? So remember that it's the distance. How far from 7, how far from 0 is 7? 7 is 7 units from 0. The absolute value of negative 12. Negative 12 is 12 units from 0. The absolute value of 0. Well, 0 is 0 units from 0. And the absolute value of 3 pi is 3 pi. Whatever that number is, that's the distance it is from 0. Inequality symbols. Hopefully you've seen some of these before. Less than, greater than, the less than or equal to, greater than or equal to, and not equal to. These are the symbols that we use in inequalities. And what we say is that if A is to the left of B on the number line, then A is less than B. If A is to the right of B on the number line, then A is greater than B. Here we are asked to insert the symbol less than or greater than to make the statement true. We wish to compare negative 8 and negative 10. Well, if we consider our number line, with here's 0, there's negative 8, there's negative 10. Negative 8 is to the right of negative 10 on the number line, so therefore negative 8 is greater than negative 10. 9/25 and 3/8. This is a little tricky when we have to deal with fractions. There's a couple of different approaches we could take, but I think the simplest one is to rewrite them so that they have an equivalent denominator. The LCD for 25 and 8, the LCD of 25 and 8 is 200. And I've shown how to do this in a previous section, section 1.2. The LCD of 25 and 8 is 200. So if I build up the first fraction, it would give me 72 over 200. And if I build up the second fraction by a factor of 25, that would give me 75 over 200. Now that they have an equivalent denominator, all we need to do is compare the numerators. 72 is less than 75, so therefore 9/25 is less than 3/8. The opposite of negative 12 and the opposite of the absolute value of negative 12. We need to be careful here. The opposite of negative 12, that's that double negative thing that we saw earlier. The opposite of negative 12 is 12. We have to be careful on the right-hand side because these are not parentheses. These bars, remember, mean absolute value. So we have here the absolute value of negative 12 is 12. We want the opposite of 12, which would be negative 12. And 12 is greater than negative 12.